So let's talk about the physical state of a substance from the point of view of phase transition diagrams. And this time around, we're actually going to incorporate the idea of heat in association with such physical transitions. As you may remember, we can plot pressure versus temperature for any substance. And when you do that, you end up creating a phase transition diagram that tells you information about whether your substance will be a solid, a liquid, or a gas. In addition, you have these boundary lines, the melting point boundary between the solid and the liquid, the boiling point boundary between the liquid and the gas, and the sublimation point boundary between the solid and the gas, which basically tells you at any given pressure, if you change the temperature high enough, you could actually undergo the transitions from solid to liquid, liquid to gas, or solid to gas, depending on what pressure you start with. Alright, so each one of these processes can basically be investigated. So you could go in those specific trajectories from solid to liquid, or liquid to gas, or you could go directly from solid to gas. And if we concentrate on the first one, turning a solid into liquid, there's actually three events that are taking place. On the first hand, the solid is being warmed up until the melting point. And at the melting point, the solid begins to turn into liquid. Once all the solid turns into liquid, then if there's any residual temperature, you can start heating up the liquid up to the final temperature. So we're going to look at that, and we're going to convey this idea with a better graph, one that instead of looking at pressure versus temperature, instead looks at temperature versus energy. And for this to work out, what you need to do is account for the melting point temperature of the substance. Now in the case of water, the melting point is 0 degrees Celsius. And this is a temperature I'm going to expect you to remember just for water. Any other substance for which a phase transition diagram is invoked will basically have to be given in terms of the melting point and boiling points of that substance. But for water, I need you to know and want you to know that the freezing point or melting point is 0 degrees Celsius and the boiling point is 100 degrees Celsius. Alright, so what you basically do is in your temperature versus energy graph, you input the value of the melting point and you have this dotted line as a reference going completely horizontally. Alright, now if you start as a solid, by definition you are at a temperature below the melting point. If you're a liquid, you're at a temperature above the melting point but below the boiling point. And if you're a gas, you're going to be at a temperature above the boiling point itself. Alright, so in the temperature versus energy graph, what that means is that you're going to start at some lower temperature below the melting point, and you're going to go up until you hit the melting point itself. Now notice that here I have drawn the line with a positive slope. That's because the temperature of the solid will increase up until the melting point in terms of its energy also increasing. In other words, this is the same thing as saying that increase the temperature, increase the amount of heat. And we know that because Q equals mcat. And I'll get to that in a second. Now, the moment you reach the melting point, at the melting point, the temperature will remain constant until all of the solid has turned into liquid, but this will take some extra additional amount of energy. So notice that we're actually moving in the horizontal, which implies that the energy is still increasing even though the temperature remains constant. But the moment that all of that solid has turned into liquid, now the liquid will start increasing in temperature, meaning that you have this positive slope to give you, the final point, the final temperature. So we're actually going to have three energy sources to be concerned with. Alright, so let's make this a little bit more clear. So once again, this is water, and the initial temperature is going to be at a temperature below the melting point. The final temperature is going to be at a temperature above the melting point, but below the boiling point. So we're still dealing with a liquid. And so what happens is that we break this apart into the three regions. The first one right here, Q1, is actually given by the mass of the substance times the specific heat of the solid times the change in temperature. And the change in temperature for Q1 is actually temperature at the melting point, so that's your T final, and the initial temperature at which you started the process. The same thing can be said for Q3. Q3, the initial temperature is the melting point temperature, and the final temperature is the true final temperature of the process. Okay, so T final, T initial. That will be your delta T. But notice that for the Q equals MCAT, the heat capacity has to be that of the liquid. So keeping in mind where you lie in terms of the melting point and boiling point is crucial so that you don't end up selecting the wrong heat capacity because their values are actually different. Now, for the region where the solid is turning into a liquid, in other words, the melting point, here you're going to use something we call the enthalpy value, the enthalpy of fusion. And the idea with the enthalpy of fusion is that the value is actually in kilojoules per mole. So you're going to have to multiply this value not by the mass, but rather by the moles of the substance. And this implies that you're going to have to take the mass, using conversions, turn it into moles. Alright, so let's take a look. Now, a proper problem will tell you, will ask you how much heat will require to take 18.02 grams of ice from -5 to 37 degrees Celsius. Alright, so first to end, we have the heat capacities of the solid, the liquid, and the enthalpy of fusion for water, which once again is in kilojoules per mole. Alright, so we start the process. Q1 is the mass, that's the specific heat capacity of the solid, which is 2.064, so we have that in there, times the change in temperature, and this is T final minus T initial, T final being the melting point temperature, pretty much the process where Q2 begins to happen. So melting point temperature, which is 0 degrees, the initial temperature is your -5 degrees Celsius, so 0 minus 5 is the same thing as 0 plus 5. Carry out the summation followed by the multiplication and you'll find out the value of Q1. Now for Q2, what you have to do is take the 18.2 grams of water and change it to moles using the molar mass of water, which is also 18.02. So you actually are dealing with 1 mole of water. But this gets to be multiplied by delta H, is 6.01 kilojoules per mole. Then finally Q3 multiplies the mass by the heat capacity of the liquid, which is 4.184. And the final temperature, which is 37 according to this, minus the initial, which is the 0 degrees Celsius, the point where Q2 ends and Q3 begins. Alright, so needless to say, everything cancels out except for the joules or kilojoules. So initially, Q1 and Q3 will give you the answer in joules. Q2 will give you the answer in kilojoules. So here I would recommend turn Q2 into joules, multiply by 1000, and then add them all up together to give you the final value, which should be 8986 joules worth of energy. Alright, we're going to do one more example. For this example, we're going to add an extra step, but this time around we're going to go backwards. Instead of going from solid to liquid to gas, we're going to go from gas to liquid down to solid. Alright, so let's see what happens in this aspect. Now here we actually have 5 steps altogether. The first step is the gas cooling down up until or down to the boiling point. At the boiling point, the gas starts turning into liquid. That's the second event. Once everything has turned into liquid, the liquid begins to cool further until it reaches the melting point. That's the third step. The fourth step is the liquid freezing into a solid, and once all that liquid has turned into solid, then the solid begins to cool down to the final temperature. So in terms of the graph, what you need to do is, once again, reference the graph in terms of the boiling point and the melting point of the substance. This is in regards to water, but these numbers can change if I give you a different substance, so don't automatically make this 100 and 0. Make sure that you're dealing with water for those two numbers to be as such. Otherwise, you will have to use a different substance. Alright, now, the initial temperature, as you'll find out, is going to be greater than 100, so we're going to lie above the boiling point, and the final temperature is going to be below the melting point. Alright, but when you have the boiling point and melting point temperatures in your graph, have your segmented lines there for reference. Because what you're going to end up doing is, starting with the initial temperature, you're going to go down, but you can only go down up until the first horizontal asymptote, which in this case is the boiling point temperature. That represents your Q1, and since the temperature is changing, you use MCAT, M times the heat capacity of the gas, since you're above the boiling point, times the change in temperature, which will be the boiling point temperature, that will be your final, minus the initial temperature. Then the gas begins to condense into a liquid. So here we're going to use a different delta H value. This is no longer delta H fusion, but it's actually delta H vaporization. And the idea is this: vaporization implies that a liquid is turning into a gas. But here we're doing the opposite. We're taking a gas into a liquid. So we're going to place the negative sign here to implicate that we're doing the opposite of the process. All right, after that, the liquid that you just formed begins to cool down. And because the final temperature goes way past the melting point, this means that you're going to go directly from boiling point all the way down to the melting point. And that becomes the third event, in which case you multiply the mass by the heat capacity of the liquid. And we know this to be the liquid because the temperature now lies between the boiling point and the melting point. Okay, and the change in temperature will be, well, melting point minus boiling point. Okay, at that point, at the melting point, you start freezing your liquid. And here you use delta H of fusion, but because fusion implies that a solid is turning into liquid, and in this process we're doing the opposite, turning a liquid into solid, we're going to multiply by not just the moles, but the negative of the moles to implicate that we're doing the opposite of fusion. Alright, and finally, you take the temperature all the way down to the final value, from the melting point down to the final temperature. Okay, and here don't forget to use the heat capacity of the solid. So all in all, we have 5 regions to consider. Okay, so here's all the information. We have, once again, water, 18.02 grams, starting at 170 degrees Celsius, which is above the boiling point, and we're going down to negative 10 degrees Celsius, which is below the melting point. So here you have the heat capacity of the solid, that of the liquid, the gas, delta H of fusion, and delta H of vaporization, and the last two values are in kilojoules per mole. Alright, so when you set up the equations, all you have to do is input the numbers. The masses are 18.02 grams, and because this is water, you will be dividing by 18.02 grams per mole to get the moles. So for Q2 and Q4, you will have the 1 mole of water as a result of the fact that you're dealing with 18.2 grams. If you had a different mass, you will have a different number of moles as well. Alright, so 18.2 grams get multiplied by 2.026, which is the heat capacity of the solids. Change in temperature, initial was 170, final is 100, and that's what we have here, 100 minus 170. For Q3, we're going from the boiling point down to the melting point, so the final is 0 degrees Celsius, the initial was 100. For Q5, we're going from the melting point down all the way to the final temperature, which is negative 10. So negative 10 is the initial, is the final, and 0 is your initial. Alright, now the only extra feature that you have to be careful about is that negative in front of Q2 and Q4, because the delta H does not have the negative popping up directly, so you have to artificially place it at the end. And when you carry out the calculations, you're going to find out that all the values are negative, and this is kind of a dead giveaway that you may need to put a negative in front of Q2 and Q4, because either all of the Q values are negative, in which case the temperature is going down, or all the Q values are positive, in which case the temperature is going up. Alright, so now the last thing that needs to be done is convert the kilojoules to joules, multiply everything by 1000, and now you add them all up together to give you the final value of negative 60,473 joules, which, if I ask you to, you could divide by 1000 to give the value as kilojoules itself, so negative 60.5 kilojoules, or whatever the sig fix may be. Alright, now with this example done, I think we are good to go. We'll definitely do more during discussion sections, so if this is not making total sense, rewatch the videos, try to do a few examples on your own, but bring your questions over for discussion section. So I'll see you then.